Okay, I had to go back and re-record this because I realized the microphone wasn't working the entire time. So I probably have two videos links on this. So this was related to advanced dimensionality reduction. Basically, it refers to like a technique used to reduce the number of variables or features in a data set while pretty much retaining the relevant information as possible. So these methods are particularly useful when dealing with like high dimensional data where the number of features is large relative to the number of observations. So, you think about image processing and text mining and things like that. Other advanced techniques often go beyond just a simple linear transformation. So, in this example here, you do all your imports, pip installs, import your libraries to get all of that. Um, all of, your sklearns and your UMAP. So in this case, there's different goals of the advanced dimensionality reduction, like eliminating reduction, improved efficiency, things like that. Then there's a couple of examples of this advanced technique. So we start out with the basic, creating a generic Swiss roll. Um, Here we identify the colors and things like that of what in the in samples, the number of samples. So it's going to take a sample set of about 1,000 and define your X and Y axis and plot those values. So this is the original 3D Swiss roll based on that data definition. And we have our X and our Y values here. And it's a 3D three dimensional image of it. Then we want to go ahead and kind of use that same data set, but just create different random states of the same thing. So you have different nonlinear methods, such as the TSNE and the UMAP. So here we have an example of the TSNE projection, which focuses on preserving the local structures in the data, often used for visualization. And then a UMAP structure, which is similar to TSNE, but it's a little faster and scalable and preserving both the local and the global structures. So then also what was demonstrated here was the LLE example, the locally linear embedded example, which aims to uncover the lower dimensional manifolds embedded in higher dimensional spaces. So you have it more clustered, as more dense population. You can actually see how this and it's basically a representation of the same Swiss roll originating, but it's plotted in an LLE format of a Swiss roll. Then you got the isomap projections, which was also one of the ones that we discussed in class. That's demonstrated here. That's plotted. MDS production Swiss roll. And the randomized PCA. So the PCA, principal component analysis, and sparse. What you could do sparse. This one is randomized, and it has kind of like the structure of the roll, but you can actually see in terms of the color differences in terms of the dense, where the data plots for each your figure size of 8.6. This is basically how we define how the graphic of it, but the components that's used here um, is randomized, and then the kernel PCA, and this was also another um, dimensional data plot that was used. The factor analysis, the projector Swiss roll, which has more of the, as you can see, the plotted, the way it plots, it has the data more concentrated, more linear, kind of like a line type, not linear, but a line versus having it in the 3D scale model. It's for factor analysis. than the autoencoder, which here you can, it demonstrates the loss of each iteration. So it's going through each iteration down, and you can actually see the loss deviation from each step. The autoencoder, the additional example that was provided that I tried out was the Hessian LLE projection of the Swiss roll, which is a different type of linear, locally linear embedded type. And that was it. Thank you for watching. How do you turn this off? You scared the mess out of me. No, don't do that to me no more. Where is that at? Doing. Just stop doing too much.